Okay, great, cool. All right, we're gonna go ahead and get started. Woo! This is a exciting moment for OpenAir and for the team you're about to meet. This has been this project that we're going to be talking about today, and hopefully involving as many of you folks as possible, and has been a kind of a long in the making. Kind of extends back to even some of the earliest days of OpenAir. And so what we're here to do is kind of a twofer. It's kind of to announce the launch of Carbon Crowd, which is a new mission platform from OpenAir, which I'll describe in some detail in just a few minutes. And the very first project that's going to be featured on this platform, Epiphyte, which we're going to go into significant detail about that over the next hour. And my name is Chris Neidl. I am the moderator today, or MC. I'm one of the co-founders of OpenAir. And you're going to meet the Epiphyte team, who's really going to take the reins in just a few minutes. But what I thought I would do, just to kind of set us up, is to give a little bit of a background first on OpenAir and Carbon Crowd and how that sort of leads to the Epiphyte project. And then you'll hear from a great group of OpenAir members who are going to talk to you about Epiphyte and what it's all about and how you can get involved. So just to quickly start off, a couple of fundamental OpenAir things. So many of the people who are joining today, certainly everybody who's on the panel is a member of OpenAir. But for those of you who are new to it, OpenAir is a all-volunteer distributed action network focused on advancing carbon dioxide removal. And we work a lot on advocacy projects where our members create bills and get them introduced. We've generated 11 or 12 pieces of legislation and 5 laws. But another big part of what we do is what we call R&D. And so this is more folks on the sort of technical maker end of our community who are coming up with different open source carbon dioxide removal innovations and prototypes, and they work on those together in an open source fashion. But first, why do we care about carbon dioxide removal? Just a quickie that I think is important to stress. One is that we need to do it. You know, according to the UN IPCC, we now have put too much carbon dioxide in the atmosphere, where we can't just reduce emissions now. We also have to take carbon dioxide out of the atmosphere. So OpenAir was really formed in response to that imperative. This is just a very well-traveled graph that sort of shows you that, which I won't really get into, but it shows all of the carbon reduction that we need to do in the coming decades. And then below this blue line shows how we also have to do negative emissions as well in combination. So the key thing, just to sort of set up what we're going to talk about specifically, a specific form of CDR today, but a really important thing to note is that carbon removal or carbon dioxide removal is many different ways of doing that, different technologies and methods. Some take place on land, some will take place in the ocean, some are really large and centralized, some are relatively small and distributed. And when we think about carbon removal, many people think about trees and soil, which is a good thing to think about. That's a natural way of taking and storing carbon. But in order to meet the needs that we need to, per the IPCC, we have to implement a lot of other forms of what are called novel carbon removal. So those are things like storing durable biomass and storing it for long periods of time, and things like biochar or tree burial, various different methods that involve the mineralization of CO2 that's in the air and turning it into a solid or a stone, and then a whole bunch of fascinating things that take place in the ocean, such as ocean alkalinity enhancement. But the pathway that maybe gets a lot of news and maybe is sort of also somewhat misunderstood or not sufficiently understood that many people are hearing about now is direct air capture, or DAC. And that's relevant to what we'll be discussing today. Direct air capture is just purpose-built machines that chemically bond with the CO2 in the air. And one of the reasons why DAC is such an interesting possibility is because it has a huge potential to take a lot of carbon out of the air at scale, up to 40 gigatons per year. We currently emit, I think, just under 60 gigatons of CO2. So it's a really very, very high potential to potentially take carbon out of the air. And in recent years, we've started to see projects actually be realized. This is the first of its kind from a couple of years ago. I think it was actually 2021 in Iceland, Project Orca. But now we have 2 projects being built right now in the United States that are much larger. And the federal government just announced a huge grant and funding round for direct air capture projects that'll take place all over the country over the next few years. So it's definitely moving, but for DAC, we really have to do a lot of things this decade to make it viable and to potentially hit that 40 gigaton or somewhere thereabouts in the coming decades. Lots more R&D and innovation have to happen to make the technology perform better. We need to reduce the energy and resources that are required to build and operate DAC. And we need to really bring the cost down from where it currently is as a new technology to where it has to be in order to be really, really high impact. And so in order for this to happen, we need to move really, really fast on all of those fronts. We need to involve a lot of creativity and novel thinking to overcome the technical and business and implementation challenges that DAC is going to face. And what we think is we need a lot more people participating in contributing to ideas and implementation. So more participation. So who is going to do that? Who will drive those needs? Certainly, and what will it look like? When will it happen? Where and how? And certainly, we're excited to see that the actual carbon dioxide removal ecosystem is really evolving very, very quickly. So there's a lot of smart people, more so every day, working on this as CDR companies and direct air capture companies, all sorts of researchers and academics, people in companies who want to buy carbon removal, and increasingly a lot of different nonprofit organizations like OpenAir that are advocating for it. And certainly the government. Government has a huge role to play in funding carbon dioxide removal. But we think that the formal ecosystem by itself is probably not enough to allow us to sort of move as fast as that we really have to. And so what OpenAir is really premised on is how do we create opportunities for the broader public to potentially directly contribute to the future trajectory of carbon dioxide removal and direct air capture specifically. And so our community is based on open source peer production. So as you'll hear today, the Epiphyte project is we want to publish the designs for it and how to build them and put them out in the public domain so that anybody could potentially build or modify their own in the future. We think that level of exposure and transparency and access will play an important role in speeding things up. And then peer production is a term that basically means when volunteers who are intrinsically motivated, that they want to contribute, it allows them to add their knowledge, their insights, and their times to co-create the things that we make here in a network in a voluntary fashion. This is a quote we really like, which you'll see again in a second. So when we think of the who, what, when, where, and how, we think of who, everyone, or the maximum amount of people. What, can we open source technologies and allow other folks to contribute to their evolution? Now is when we want to start it and to move fast. Where, everywhere, where we can build our community. And how is through that peer production type of model where you have many different people contributing to common goals over time. And so this is what the mission that I mentioned at the top that we're launching today, Carbon Crowd, is really, really about. It's an OpenAir mission. And I'll drop these links once I get off my presentation, and we'll share with everybody tomorrow the recording of this along with these links. But what Carbon Crowd is a website right now, carboncrowd.cc. And the idea is it's a platform where some of the open source CDR technologies and innovations that our members are making, they can post them there and then collectively build their prototypes with input from many different people around the world. So it's meant to sort of enhance the number of people who are actually contributing to these types of projects. And the way that it basically works, before I wrap up, is that all different solutions that are posted on Carbon Crowd come from the OpenAir community, and they're all published under open source licenses. That's a requirement. And the focal point or the main activity of Carbon Crowd is that over 2 month, what we call build cycles or builds, we will every 2 months build a new version of our technologies and keep going and going and going with a different main team doing the building for that 2 month process at a particular place, with input and ideas coming in from the broader Carbon Crowd OpenAir universe in terms of solving problems, optimizing ways that we do things. And every 2 months, it'll be handed off to a new team, and some new optimization theme or goal will be the focus of each new build. So for the first one that you're going to hear about today is just the very first one where we build the very first Epiphyte. But in subsequent ones, we might want to make it larger, or we might want to make it smaller, or come up with a novel way of reducing costs or using the CO2, and just keep doing that every 2 months forever, or as long as we want to. and have a different team somewhere else in the world lead that. And then again, the build teams will be supported by hopefully a much growing, more diverse, large worldwide community who can provide their knowledge and insights as we go. Build themes and teams as we get towards the end of a build cycle, a 2-month build cycle. We'll start to take in ideas for the broader community about what would be the next thing we could potentially do based on what we just achieved. And then there will actually be a voting process whereby the community can register which ones that they think they'd like the next one to be. And then materials are actually, we have a kind of a $5,000 maximum we want to keep as a constraint for any project. And right now, OpenAir does have some resources to fund the next few builds for the project we're going to talk about. But ultimately, as we grow, we'll put in a crowdfund option where people can subscribe, and any money that we bring in, we can build one or more units for every build cycle somewhere else in the world. And so we think that this will be sustainable as it goes. So I'm going to be quiet right now. And what we're excited to do is talk about the inaugural Carbon Crowd project, which is called Epiphyte. And this is an open direct air capture machine. And I'm very pleased to welcome, if everybody wants to turn on their cameras and their audio, the amazing group of people that have been working on this for many weeks and months. We're going to hear from them, and then they're going to tell us a little bit about their project. So, hey, everybody, how's everybody doing?
Good.
Excellent. Very, very cool. So what I'm going to do is just before you guys get into and talking about the project, let's just do a quick round of introductions for the folks who are on the team right now. And I'm just going to pick them as I go. So I'm going to start with David Wilson, who joins us from Philadelphia, PA. Hey, David, how you doing?
Good. How are you? I've been working with OpenAir as a volunteer for about 2.5 years now, and I'm an electrical engineer.
Excellent. And again, based in Philadelphia. And then also joining us from Philadelphia, we have JP Hennessy. Hey, JP.
Hey there. JP Hennessy. Joined OpenAir about 2 months ago, and probably due to co-location, was able to join in for this first Epiphyte project. My background is mechanical engineering and material science, with some experience in different types of CDR research.
Fantastic. And we got Seth who's joining us as well.
Good morning. I'm Seth, based out of Washington, D.C. I'm working as a product manager on a lot of sensing and AI applications. So, we're trying to keep things pretty basic on the sensors in this first build, but they're going to become really important as we head down the line.
Excellent. We got Ling, one of the OpenAir OGs, who's been with us for a long time. Hey, Ling, how are you?
Hi. Yeah, I'm Ling. I'm a biomedical engineer. I work in biotech. In the past, I worked on mechanical things, design, systems engineering and stuff. Right now, I work on software, and then I help with the CADs and just like random things in Epiphyte. Oh yeah, and I'm from San Mateo, California.
And you designed our logo, which we're looking at right now. So
Thank you. Yeah.
A person of many talents. And then last but not least, also joining us from Philadelphia and joining us from the site where we're actually building the first Epiphyte, the University of Pennsylvania, we have Chuck Pearson. Hey, Chuck.
Yes. Hi. Good afternoon, everyone. I'm Chuck Pearson. I have a background in commercial and institutional HVAC and mechanical system design and sales, and also building controls. And so I'm here to help sort of be the boots on the ground, do the nuts and bolts piecing together of some of these materials that we've purchased and hopefully we'll be assembling here shortly. And and we're joined here just now. Can I introduce you? This is Mary Lynn Huff. Dr. Huff is the director of the UPenn Chemistry Lab.
Chemical Engineering Lab.
Yeah. Sorry about that. I didn't have a statement prepared. So she has graciously donated this space here for us to help give some physical space for us to actually do the construction.
Yeah. And Marilyn, first, let me just add to that a little bit, just extend our enormous.
Hey, Chris, can you hold 1 second? I'm on headphones. Can I put you on the speaker?
Yeah, sure. Absolutely.
All right. Sorry.
So while we do that, I just want to let me know when you can hear me, Chuck.
Not that.
Great. I just want to give just the most full-throated expression of gratitude for Dr. Huff and for UPenn. This is the first time we've done that. We reached out because of the department's and the university's important connections to CDR right now and historically. And we were just blown away by the willingness for Dr. Huff to host us for this and how aligned we were on the nature of the project. So really want to thank you, Dr. Huff, and your team for putting us up here for a couple of months. And please feel free if you have anything you want to share about the department or what drew you to the project.
I don't have anything to share right now. I am happy to have you guys here because it actually does fit in nicely with some of the experiments that I was trying to add to the undergraduate experience as we are working to kind of shift towards more sustainability oriented projects. So this is a kind of a win-win for us, I think.
Excellent. Well, really excellent to have you here and excited to have you involved. And, would love to have you or Peter or other members of the community on for future webinars that we're going to do biweekly, but really huge appreciation for your partnership.
Great. All right. Thank you.
Great.
I'm going to hand it back to you, Chris.
Yep. Sounds good. So I'm going to stop yapping and
thank you so much. Appreciate that.
We will have a Q&A for all of you to ask questions as we go. And we'll have a little bit more of a dialogue with the members of the team about the goals of the project. But to get things going, I think we'll start with David Wilson. We're going to go ahead and give an overview of the project objectives and then the design that we're starting with. So David, you want to take it from here and let me know when to advance the screen?
Okay, I'm going to pass this slide to Seth because he came up with the wording.
Yep, I'm going to jump in here. Yeah, so, Chris talked a fair bit about the goals and objectives of the Carbon Crowd mission in general. And so those certainly apply here. And we've got some very specific objectives around Epiphyte and how that ties into the Carbon Crowd objectives. So, the first is simply to prove out the theory, right? To be able to demonstrate room scale open source direct capture is a viable thing. Everything that's out there right now are these commercially available, these gigantic projects, pulling in megatons, and we're looking to see what we can do with a small scale purpose-built operation. We want to improve, right? Optimize over time. We're gonna successively do these different builds, looking to optimize and improve on different things and really see where we can go and have the kind of flexibility and agility that the bigger corporate sponsored DAC can achieve. We want to build out the data, right? Data is gold these days. And so we want to build out as much of a data set as we can around DAC to support future operations, to support experimentation. Part of this is we're going to have an ever-growing set of these machines around the country, around the world, different locations, different conditions, different operating parameters that we can set up some real interesting experimentation around. We want to seed for the future, right? Matt just posted in the chat a link to the carbon removal challenge. This Epiphyte platform that we're building is a great seed effort for teams to come in and use any of these iterations of an open source machine to build out their own ideas. And then, the next two are really, really important to the success of DAC and CDR in general. And those are outreach and education, right? There's a lot of pushback in some parts of the community to DAC and CDR, and they don't really understand what it means. So part of what we're doing here is to reach out and make this available, make it familiar and something that people can come in and touch and explore, whether on their own or as part of a formal education as a school resource.
Excellent. Thanks, Seth. And I think I'm going to pass off. And we should also say the name, Seth was the one who proposed that. Epiphyte. Seth, what's an epiphyte for those who don't know it?
Yeah, an epiphyte is a plant that lives symbiotically on another plant. And what's interesting is that it does this without extracting resources from its host. It draws all of its nutrients from the air. So, colloquially, it's known as an air plant. So for us, the name was a play on that, pulling the air from OpenAir and the plant, because it is, the OG DAC machine.
Yeah, exactly. Great. So we'll hand it back, I think, to David, and maybe we can talk just a little bit about the inspiration design wise, a little bit of the kind of background there. So David, do you want to take it from here?
Yeah, this project that you see here is called Thursday, and it was built by a company in Kenya called Octavia, and this is their first prototype, and it's probably 15 to 20 feet long. I'm not sure, but you'll see as I go on a lot of commonality between their design and ours, because it was the seed that our design came from. And what we hope to accomplish with Epiphyte is to build something that's a little smaller, less expensive, and to solve some of the problems that the Octavia team identified with their method. So let's go on to the next one. This is the eventual plan for what Epiphyte is going to look like at a high-level schematic. And I'll get into the details of that later on, but that's just a brief schematic. Next. It's built with off-the-shelf components. And this is what's great, having an HVAC expert in our group. Thank you, Chuck. He was able to find, so we didn't have to actually bend sheet metal ourselves, and these components can all be ordered relatively inexpensively. And they're all standard HVAC components that are like the guts of this build. A filter box, which is going to be the sorbent chamber, dampers, and fans. Next. And then the most important high-tech aspect of this, I guess you could call it, is the sorbent, which is the material that actually absorbs the carbon dioxide. And we're starting with one that's available off the shelf called Zeolite 13X. And it has a lot of uses, but it's also not ideal for the long term, but we will be looking at other forms of sorbent when they become available. The key thing that this material does is, and the whole family of sorbents that we're looking at, they absorb carbon dioxide when it's at room temperature and standard atmospheric pressure. But then when they're subjected to heat or a vacuum, they release the CO2. So it's called, the whole method is called temperature vacuum swing adsorption. And we'll go into the next one now, and I'll show what the cycle looks like. So in a way, this machinery is going to breathe in carbon dioxide and then breathe it out. But the first phase of its operation, it's going to, the fans will turn on and the dampers will be open, and it'll just blow a massive amount of air through the system. And as the air goes through the sorbent, which is in the form of a powder held together with metal panels, it will absorb the carbon dioxide, which is coming through at standard temperature and pressure. So that will run for, we don't know how long. Part of our experimentation is going to be how long does it take, and at what fan speed is it necessary to get the most CO2 captured. And then next, the chamber evacuation, which is where we close off the dampers and shut off the fans. And there'll be a vacuum pump that will suck out as much of the air as we can get from the chamber. And one of the other things we're looking at is how much vacuum can this, the construction of this particular project handle. But we'll try to get as much of a vacuum as we can. And that will allow space for the CO2 to be released from the sorbent panel. And then next, we have heaters built in that will heat up the sorbent. And so in the presence of the vacuum and the high temperature, the zeolite or whatever sorbent we're using will release the carbon dioxide back into the chamber. And then once it's heated up in the next picture, this is a diagram that shows, just as an aside, what the sorbent panel looks like. Now, this is like end on. The air would be going, say, into the picture through the sorbent, which is built in a panel, and there will be resistive heating wires to heat it up. And these wires are made of a resistive wire, which is similar to what you would see in a toaster oven or in an electric stove. And I believe that JP is going to show us a little more detail about how the sorbent panel is built.
Yeah, sure thing. So here will be a quick video of the different components. So the centerpiece is going to be where the sorbent will be placed. There'll be a screen that holds the sorbent in, and then an overall faceplate that will keep all the components together. Similarly, on the backside, after that center area is loaded with sorbent, another screen will be placed on the back, and then another back panel there. So we really tried to design for modularity so that this could be reconfigured in different ways. We can make it bigger. Others could work with different faceplates. And at the start, tried to build it such that we could use as few components as possible. So kind of a fun build. Ling and I worked together. She challenged me to look at it in different ways to make sure all the pieces worked right, and then built all the CAD for it. So she did a great job here.
It's beautiful, by the way. I got to say, Ling, well done and great design, JP. But looks extremely cool. So it's great.
Thanks.
So back to our cartoon pictures here. We'll start pumping CO2 from the chamber in the fourth phase, which is the CO2 extraction, and the CO2 will be released from the sorbent panel that JP just showed, and it'll get pumped into a tank where we can capture it, measure it, figure out what to do with it. The usefulness of the CO2 that we're able to capture will depend on the purity we're able to get, but that's one of the things we're going to be studying and trying to optimize. And after the CO2 is released from the sorbent panel, we'll remove the tank and use the CO2 and then start back over again with the first part of the cycle. Now, here I want to show the machine that I've been showing you is the completed project, which we're not anywhere close to yet. So we're building in phases, and in each phase we have something we want to accomplish before we move on to the next. Phase one we're calling Hello World, because really all we're going to do is blow the air through the sorbent and see if it is actually capturing CO2. And the way we do that is you're going to start seeing these colored squares that I've added. Those are electronic sensors, and this system is going to depend a lot on the sensors and being able to read them, because they're the ones that tell us, for example, if the sorbent is working. If we measure the CO2 concentration coming in and the CO2 going out is less, then that means that some of it's being captured. So when we're actually running the completed system, for example, we might have an algorithm that measures both the CO2 in and out. And when the output is back to the same level as the input, that means that the sorbent has absorbed all of the CO2 that it can, and it's time to start releasing it. So that's our first build that we'll be doing in the next few days. And then phase two, we'll turn on the heaters and see if how well the CO2 is released. And you see a lot of temperature sensors there, and that's because another thing we want to research is the efficiency of the heating system. Since we're building it from scratch, we want to know how fast does it heat up? How do we control it so that it doesn't get too hot and cook the sorbent? How long does it have to run to accomplish what it needs, and how can we make it most efficient? And then phase 3, we'll add the vacuum pump, and we'll be able to see what happens when we increase the level of vacuum. So we'll include pressure sensors in addition to the others. And also, I forgot to mention, there are also airflow sensors on the input and the output. And for measuring the flow of air, we can find out the important data on how much air actually gets passed through the system to capture a certain amount of CO2, which can tell us how effectively the system is working. And then finally, phase 4, the full design, it's going to be under an automatic control of a microcontroller that will not only shut the pumps on and off and open and close the dampers, to read the sensors and run an algorithm that should step the system through the different phases of its operation. And maybe most importantly is gather data on how to optimize the system. It can tell us how effective the whatever sorbent we're using is, how much energy we're using, how long we should run the fans and how long we should run the heaters. So it'll be a big research tool, and I am expecting that it'll still be useful after it's built and demonstrated for people to keep on doing research with. And next. This is just a view from a couple of weeks ago as I started working on the electronics. Most of the parts that I'm using with the first build, I bought from Adafruit with a processor. It's an ESP32 Feather controller. It's a fairly powerful little chip that also has a built-in Wi-Fi and Bluetooth, so we'll be able to communicate with it, hopefully from not even when we're not even present. It's got a display. All the sensors are connected with I2C. Okay, next. And this is our lab before we start moving it in. On the left is just a view of the chemical and biomolecular engineering lab at Penn, and the right one is where we're going to be working, and the next page shows Chuck starting to assemble the first things that have arrived. And I think we're going to switch over to Chuck now to give us a little tour.
All right, I will do my best. I haven't rehearsed anything, but I'm going to aim this camera down a little bit. So one thing I wanted to touch on real quick that may seem very, I don't know, like really getting into the weeds on something that doesn't matter is this cart. The original design from Thursday that we're basing most of this on, they had built their own base to put everything on, and they were using that base as their vacuum chamber and where they were storing the CO2 that was coming out of the sorbent panel. And what we decided actually quite recently was, well, let's buy something that's already, fabricated that we can set all of this on. And instead of building our own, hermetically sealed tank for storing the CO2, let's just buy a tank, like a refrigerant tank. And we can set that down here. And another thing is, this gives us a place to, attach everything to. We can put all of the electronics down here, and then we can, move it around. It's already on wheels. And so right here, we have the basic components. I have another damper here. So basically, this is the sorbent chamber, which is, a repurposed filter box. And it's pretty basic. It just has a 2-inch thick filter in here that slides in and out. And the idea is that we will use, let me see if I can get this out just to demonstrate. This fits in here very tightly. So you'll see the plan is we're going to build cartridge like this that can slide in and out. And this is what Ling and JP designed, was the sorbent panel. And so the idea is we can pull that panel out, and if we need to change the sorbent type or maybe change the size of the opening in the sorbent panel, we can easily get in there. We can also open this up and get to our sensors and to the heater and everything. Because these ends will be sealed up with this damper attached and the fan attached. The original design had a fan on each end, a fan on the inlet and a fan on the outlet. I think in version 1, we're just going to have the one fan attached on the downstream side, so it'll be a draw-through configuration. And so we'll have a damper on the inlet and a damper on the outlet, and then a fan on the outlet. And we'll control this is a really good multi-speed fan. It has a really nice controller on it that David is going to be able to program through his system, where we can, modulate the speed to test it at different airflows. We had part of this, the whole idea here is we want to have something very small and modular, but also very affordable and use off-the-shelf parts. And we were looking at using a little 6-inch diameter fan, which only did about 400 or 500 cubic feet per minute, which I think was going to be fine for this version 1. But the 8-inch fan did about 800 CFM, and it was only a few dollars more. But then for only a few dollars more, we get this 10-inch fan that can do 1,200 CFM. And so we decided, we've got this sorbent panel that is capable of, or the sorbent chamber, which is capable of moving 1,200 CFM. And so maybe for the next round, the folks that we hand this off to, if they want to upsize and go to the next level, they'll already have this fan that's capable of that. The great thing about this fan, though, is we can start it out at 200 cubic feet per minute and do all of our experiments at that level. And maybe that's the perfect level for the size of sorbent panel that we have, but then we have this expandability. Or we might find that we need to cram 1,200 CFM through that sorbent panel to make it work like we want. But so we have this flexibility built in, and that fan's only a couple $100, which makes it very affordable for this whole build. These dampers, I know that I've seen about 3 or 4 different versions of Octavia's design. And they had a damper similar to this, I think, originally. And on one of their other designs, I saw they had a very expensive valve that I would see on a pumping system. So it was like watertight, which means they're trying to pull a perfect vacuum. We don't know if we're going to need to do that. This just has this rubber gasket in it. And when this actuator pulls this closed, it's not going to make a perfectly hermetically sealed, tight seal where we're going to get a perfect vacuum. But according to a chemist we spoke to, he said he didn't think that we need a perfect vacuum. As long as we can kind of get most of the air out, we might be okay. And so for this Hello World version that we're doing, I might be able to get this damper to close just enough so that we get enough of the air out that we can then start seeing the CO2 off-gassing. If not, I can modify that damper and maybe make it more airtight. But the next phase of this is basically just to screw all this stuff together and turn it on and see what happens. And that's what I'm looking forward to, because what I want to get to is the experimental phase where we find out what's the ideal size of the sorbent panel versus how much sorbent do we put in it versus how much airflow do we put across that, and for how long, and then how much heat do we use. And all those different parameters, I'm looking forward to doing, 400 experiments to get all those data points, and then maybe build a curve to say, the efficiency point is right here at whatever airflow, whatever temperature. And then we can pass that along to the rest of the world and say, okay, we've got all these different performance curves that we've built, but it's only for this one sorbent. And so now we can give them this test bed to just pull this out, put their own sorbent in, and do the experiments again, and then kind of off and running. I think that's it, unless you have questions.
Well, what I'd say is if folks, we have a couple of good comments that are being left here, but if folks have specific questions or ideas, you can pop them in the chat. It's better to pop them in the Q&A because they're easier for me to track. But I figured I would kind of start off some of the questions here. And so why don't we give people a sense of a picture? As I said at the beginning, we're going to be building this over the course of 2 months along the lines of what David laid out. And every 2 weeks, we're going to check in with a webinar just like this. So the next one's going to be in a couple of weeks on Wednesday at the same time. But I wonder if David and gang, if you could say, what's first? What is it going to be like to build this over the next 2 months? And what are the sort of, roughly speaking, the phases of actual construction? I wonder if you could provide a little more detail for that.
Well, the first phase will be like it'll hopefully go like I showed in the diagrams. The first phase will just be turning on the fans and checking to see whether the sorbent is taking up any CO2. And then we just add on to it piece by piece. It's a little hard to say just how long it'll take for each step. That's how research goes.
Great. And the other part to that is that we're building it in Philadelphia. It's the first one that we're building. We're building it at UPenn. We have 3 of our members, Chuck, David, and JP, are all based there. What is that going to be like? And how is it that people who are local within Philadelphia, we want people to be able to drop in and help? And I just wonder if you could tell me what the kind of day-to-day or week-to-week might look like in terms of you guys going to UPenn and making progress on this. You're going to sleep there, Chuck, for 2 months, or what's the plan, at least initially?
Well, that's a good question. I do like this lab space. It's really nice. And well, my plan is to get together with JP and David and maybe just have some initial powwows here and sort of put our heads together on exactly what the game plan is on what we build first. And we'll probably be doing some things simultaneously. JP might be building the sorbent panel while I'm just trying to get these items pieced together. And, obviously, David's already started building the hardware for the controls and doing the software as well. I'm very anxious to see his little microcontroller control that fan from a PC. I'm very much looking forward to being able to, come in, open the computer, and instead of plugging that in and turning it on, being able to turn it on with a switch on my computer screen.
Excellent. And for people, tomorrow what I'll do is I'm going to edit this video tonight, and then tomorrow everybody who RSVP'd will get an email from us with that link, but there'll also be several other links, right? So there'll be the calendar where you'll be able to sign up for future webinars. There'll be a contact form if you're in the Philadelphia area or plan to be over the next 2 months and might want to come in and pitch in once or regularly. I'll connect you with David, JP, and Chuck, because that is an opportunity if people want to come by. We also have a forum that we're creating for this that's going to allow people to, once they see this or they're looking at the design docs, they can share their own ideas. And we can have an ongoing conversation happening on a forum. And that's one of the ways in which we'll enrich the design and make progress. But I'm wondering for you guys, for the gang here, you kind of laid out what the goals are of the phases in terms of what we're trying to find out. Can you also let us know, like, if people did want to contribute, like, broadly speaking, what kinds of skill sets or experience are you looking for? Are there particular things that have the biggest question marks on them right now that you can talk about that might give people a sense about how they can plug in?
Well, I would say it'd be great if we could get someone who knows how to make sorbents in their kitchen. That would be very helpful.
Sounds like
I was going to say the same thing. Maybe not in a kitchen, but maybe in a wet lab would be fine too.
Yeah.
Octavia synthesized their own sorbent. And so, there's probably methodologies, I think, for what we were doing of just seeing how we could get all the integration together. It'd be really great if this could become kind of a platform for testing and developing new sorbents. That would be really super cool, and I think is an area of opportunity for someone with that deeper chemistry type of skill set to get involved.
And we're in the right place, right? The Department of Chemical Engineering. Hopefully, some people will walk by that will have some good ideas on that. Anything else you'd want to add to sort of key areas of need that we have, or big questions? Go ahead, David.
Yeah. Yes, I would hope for somebody that could help with programming, that may be an expert, say, in user interfaces, because I'm rolling my own program to run this, but it's never going to be really that user friendly. And so eventually we're going to be leaving this behind as an educational tool. So if there's a way somebody can make it so that it's much more accessible and that people can gather the data and control the options available with it without having to program it themselves, that would be very useful.
And I think the flip side of that, David, is someone who's experienced at data visualization and analysis. So we can tie that into the back end, not just how to control the system, but to know what came out of it as a result.
Yes.
Great.
Maybe I can be helpful with that later.
Oh, great. Okay.
I'm doing software now.
I think eventually it would be good if people can be thinking about another space to donate, or make available to us, because I think once we're done with build 1, we're probably going to get kicked out of this lab, and we'll certainly be lobbying UPenn for some more space somewhere. But if there's somebody in the OpenAir collective that knows of the next spot, that would be good.
The next spot, Chuck, for the next build, or the next place to put this unit that we built in Philadelphia?
Well, if the university wants to keep this one and continue to use it for experimentation, that would be great. I think that would be a success. Yeah. But if it's not, and if they say, can you get this hunk of metal out of here, we need a place to put it, I would think hopefully there would be a group that would be more than happy to take it and work with it.
Yeah, we have some interesting developments about where the next build will be, which maybe I could talk about at the end. But real quickly here, before I just want to show something that I did drop in the links, and I wonder if you guys could kind of speak to it a little bit, is that we're using Hackster.io is the place basically for our sort of repo and documentation. So we have, a very long list of bill of materials here, all with order links. But this is the very beginning. So there'll be a lot of changes that will happen to this based on our experience of building it and the new visualizations that we produce. David or Chuck or JP, Ling, anybody, I want to know if you have anything you want to say about the current state of the repo here. Again, we want to stress it's the very beginning, but what are some other types of resources or documents that might appear on this as we progress with the first build?
Well, we're going to be putting up schematics for the electronics and also drawings for the mechanical aspects of it, and some instructions for putting it together. I wouldn't recommend that anybody go through the bill of materials as it is and just buy all that stuff, because some of these things we're just buying speculatively because we may need some extras, or we aren't sure just which direction we're going to go. So it's just getting started yet, but eventually it will be good enough instructions so you can build your own.
All right. Well, let's do this. There's some great questions that just popped in before I even noticed. So Tank Chen, who's a bit of an OpenAir superstar based in Taiwan, happy that you're joining us, Tank. He asked, can you please explain what the different parts on top of the station does or do? What purpose do they serve in the overall design? And what were some of the factors you had to consider to choose one off-the-shelf parts to choose the parts? So I don't know if that the different parts on the top of the station does. Do you know what Tank is referring to there?
I'm not sure.
If they're just asking me about these three components, I could answer that, but I'm not sure if that's what the question is.
Let me
I
see.
feel like that's what he's asking.
Yeah. Tank, feel free in the chat to elaborate. Okay, he says yes, that is what he's asking. So, yeah.
So this is what I call the sorbent chamber. I'm going to turn it a little bit so you can see. So it's basically just a box, a plenum, for the air to go through and to have a place to put the sorbent panel in. And so the sorbent panel will go here. And it just has these 10-inch round duct connections so that we'll have something to attach the damper to and the fan to. So this is, I'm going to show you this fan a little bit better. So this is a 10-inch diameter fan. It's about, you know what, I can't remember. It's probably about 1 horsepower, give or take. It has this digital controller on it so you can change the speed and turn it on and off electronically. And then this is just the damper that we're going to use so that because it is a temperature vacuum swing device, we need to be able to seal off the inlet and seal off the outlet when we're in desorption mode.
What was that?
I said it's a valve. I didn't used to know what a damper was until I looked it up. Yeah, it's a valve.
A valve,
it opens and closes, lets air in, blocks airflow.
Yes, thank you. This is an actuator, and it's just motor driven with 24 volts, and it turns this shaft to open and close that and make an airtight seal.
Excellent. So I see, Seth, you've been answering some of the questions that have come in here, and I think you're typing an answer to Michelle's question right now, but maybe, I don't know if it's easier for you to just sort of summarize.
Yeah, I'll answer that. Yeah. So Melissa was asking about the output, how much CO2 are we actually removing with this device? And the short answer is we don't know. For this first, so the Thursday device that Octavia originally built was targeting about 1 kiloton a year. For us, for this first build, we just want to see that we're capturing any, and that's a success. And then further builds, as we iterate, things like sorbent chemistry, the heating element efficiency, how well sealed and how strong a vacuum we're able to get. All of these things are going to affect the efficiency. The airflow, as Chuck mentioned, as we ramp up the fan and pump more air through, is there an increase and then maybe a point of diminishing returns? These are all experiments that we're going to run and iterations we're going to do in subsequent builds to try and up whatever efficiency we get out of this early stage.
Excellent. Thanks. I'm going to add Matt Parker, co-founder of OpenAir and kind of the OG of R&D here in OpenAir, asked a great question about the second build, which I'll hold till the end. It's also worth mentioning that in addition to Thursday, this project really kind of stands on the progress that was made with other open source CDR projects within OpenAir, particularly Violet, which was another moisture swing DAC project that Matt led for the better part of 2 years. As well as Cyan, which is a small mineralization device that helped kind of lead us to where we are right now. So Sean, another awesome OpenAir member in New Jersey, an advocate for us, asked the question, how would we characterize the optimal space and facility requirements for a project like this? We're obviously in a great lab with all sorts of resources, but at a bare minimum, what are we looking for as a venue for future builds?
Well, I think the space we have now physically is sufficient to have 3 of us in here working together and enough room for the materials and enough room to kind of move around. This area is about, 15 by 20, 20 by 30 at the very most. So, I mean, if you're really in a pinch, you could cut that in half and kind of work in a cramped environment. But that's the general idea that I see.
So an added resource that would be
okay, JP.
An added resource that would be beneficial in the future too is having connections or having students who are part of an engineering program who have access to machine shops and the machining labs, because they can get parts laser cut in a couple days for a couple bucks versus us having to send out for those parts. And so their ability to just have access to that resource and be able to prototype pretty quickly doesn't necessarily mean that the final device has to be there, but just that access would go a long way for future members of future builds.
Excellent. And we just have a few minutes left, and I do want to kind of tie it up with next steps. But before I do that, Alex, another diehard OpenAir member based in Oregon, we've talked about this a lot, but the idea of even miniaturizing this a little bit more and potentially building some of the housing with 3D printed parts. As we get into these in future weeks, we'll talk about the directions we think that this could go in. But is that crossed the your mind at any point about possibly integrating 3D printing as an element of this? We'll have Alex join us. Help us take in that direction.
I don't see why not. I mean, what 3D printing is great for is custom parts and specific designs. And kind of our mantra with this was to use as many off-the-shelf parts as we possibly can. So as we iterate, and we start to find ways to optimize that don't use off-the-shelf parts, I'm sure 3D printing will become a really important tool. As for miniaturization, I mean, this is already pretty darn small compared to the DAC projects out there. So, but, we'd love to make it even smaller. If there's I guess there's a trade-off between size and your absorption efficiency. But as an educational tool, having a desk size model would be brilliant.
Mm-hmm. Yeah, I think it would be great to build a tiny one that's a single person can do in their home, like Cyan was. That's what got me involved with OpenAir, building my first Cyan. And for those of you that haven't been around very long, it was a really small carbon capture box that you could build in a couple of hours in your spare time. And if we could come up with a way to do that with this technology, that would be really useful.
Yeah, absolutely. And one thing we'll wrap up now, and I'll just talk a little bit about next steps. But it's also worth noting, for builds that we do, we want to keep things to $5,000 or less, both to kind of keep that cost constraint, which will allow us to do regular builds. This unit right now we're kind of weighing in at for this prototype is somewhere south of $3,000, I think. Was that right, David? We might have a couple other parts to run for, but I think that was about the dollar amount.
Yeah, we're still under budget. We might need a few more things as we go along.
Okay, great. All right, the hour flew by, as it always does when you're having fun, but I want to just quickly talk about next steps. Again, the whole point of this is really to get the maximum number of people involved, providing ideas and building systems as we go. And so away tomorrow when I send, again, we'll have links to all of these here, so you don't need to worry about copying things right now. But do tune into our biweekly webinars where we'll be giving updates about where we are in the builds and then asking for direct support in areas where we need help. The forum, again, will be sent to you tomorrow. That's where a lot of these conversations, we'll be talking about software. We'll be talking about, sorbent discovery and having different people's insights and ideas. I think the forum will probably be one of the more fertile places to get involved. We have a Discord server, which I'll send the link. That's the main place, kind of like Slack, where OpenAir members hang out. And then definitely stop by if you're in Philly. And again, there'll be a link that you can sign up if you're in Philly and you are interested. I'll connect you with JP, David, and Chuck, who can give you the logistics and details of that. Matt did ask about where next. We have enough funding to build a few of these, and it's a bit in flux. And we think we might build one in Dubai, which is where the big climate conference will be. Buffalo, New York is on the list. Luxembourg, Boston, for reasons that we can get into as we go. But as we go forward for this, we want to have a kind of a voting process after we do the first few, where people can submit ideas about what would be a cool direction to take this in. And then we'll have a voting process for that'll be somewhat modified, that will determine when the next build will happen. And so I think as we get towards the end of the year, we'll get into that mode of actually presentations, or rather proposals that could be made to determine where it goes. but we want to build these all over the world. And if we raise more money through our community and other sources, we could build multiple ones at the same time for each build. So anyway, we're so thrilled about it. It's pure open air as an idea, and we're super pleased to kick it off with Epiphyte and with this team. We're just amazing, just an amazing group of people who've been contributing to this. So with that, next in 2 weeks, do join us. I'll send out the link to that. We're going to have special guests each 2 times we do this to give us particular perspective and ideas. And as we mentioned, Octavia Carbon, which was sort of the members kind of came together through OpenAir, and now they're just doing amazing things in Kenya. We just had them on This is CDR, our other webinar yesterday. And 2 of the brainiacs behind Octavia on Thursday, Mike Wandera and Duncan Kariuki, are actually going to join us. And I'm going to be in Kenya when they join us. So they'll be joining us from their workshop, and they can take a little bit of time to even show the DAC machines that they're building, but they'll be giving their insights next time as well. So, all right. Well, with that then, looking forward to having people tune in, and thrilled to get started. And yeah, we'll see people either on the forum or in a couple of weeks. So thanks everybody for joining. Thanks team.